And these are the basic three ingredients. If you have these three, almost guaranteed you're going to have a magnetic field. You need an electrically conducting fluid of some kind. And for each of these examples, it's an electrically conducting fluid. So for stars, it's a plasma, an ionized plasma, a really good conductor. Can't really get better than that, I would argue. Failings relative to a plasma. For our planet, terrestrial planets, we have liquid iron in some portion of the core. That is a moderately good conductor, good enough. For the gas giants, they have metallic. That is a liquid, and it is electrically conducting. And for the ice giants, they have ionized water, which is good enough. Well, so in all cases, you need some kind of electrically conducting fluid. The next thing is that fluid has to be in some kind of complex motion. Some complicated motion of the conductor underway. And in all of these cases, that complicated motion is what else? The fluid being stirred around in some complicated turbulent fashion. Now, people will often say, I can never just say, you also need rotation. Technically, that's not true. If you have a turbulent fluid and it's not in a rotating body, it will generate a magnetic field, okay? But it will be a very small-scale magnetic field, disordered on a very, disordered down to very small length scales. And so the rotation does the all-important task of organizing that magnetic field, large-scale magnetic field. Rotation, while it's not essential, is pretty much what we're going to want to see. Okay. Did I wear a microphone? Yes. People having trouble hearing me?
We're recording.
But they're recording, yes. And actually, okay. This is not going to be very different from the recording from last year, but that's okay. You can always have two of everything. Let's see. Clip this here. Okay. So while rotation isn't essential, it's for all the magnetic fields we care about that we're really going to be able to make use of. It's going to be important. And what we need also is that this turbulence has to be sufficiently vigorous. And so there's one figure of merit known as the magnetic Reynolds number, which we'll get into. And this characterizes the fluid and the flow. And it's a product, it's dimensionless, but it involves a product of the velocity, the linear scale, the linear size of this thing, and the electrical conductivity. So in order to generate a magnetic field, you need a fluid and a flow where this product is sufficiently big, and we'll get into how big that must be. But so you can't have something that has poor conductivity. The conductivity would be a very small number for, say, air. So we have turbulence in the air. I flew in yesterday. I will vouch for the fact that every time I fly into Denver, there's plenty of turbulence. But it's not sufficiently conductive, so the air doesn't generate a magnetic field. Right? Likewise, the water in your bathtub, which you could stir up, is a conductor, but if you multiply it out, you will not get a very big magnetic Reynolds number, so you will not be able to sit there in your bathtub and generate a magnetic field, I'm afraid. The other two factors, though, the velocity that you stir at and the size, are important. Now, I did say that the ice giants will generate magnetic fields with their water. They have size on their side, right? Those planets are much bigger than your bathtub. So that's where in space physics we often are able to see these effects, which are very hard to make manifest on the Earth. We have things that are thousands of kilometers across. The velocities are not always screaming fast. On the sun they are, kilometers to tens of kilometers per second. So that's not, that's not piddling. But in the Earth's core, very small. But when you multiply these all out, you get a big number. Okay, so that's sort of the big picture. I want to illustrate this with a toy, okay? And this has none of the ingredients I just spoke of. How many people have seen this? It's called a homopolar dynamo. seen, not a real thing. You've probably never seen a real thing. But the cartoon is pretty prevalent in discussions of dynamos. And what it's meant to be, this is my own artist rendition. It is a metal disc. Picture it being maybe copper with an axle, right, welded to the disc. And then it's a wire that just goes like that. And the disc spins, and the wire stays where it is. Okay? So this is a toy. It will generate a magnetic field, in principle. We'll be able to work that out. It is not a conducting fluid. What it is a multiple part conductor, right? A fluid has lots and lots of zillions of parts. This has 2. Apparently 2 is what you need. It is not in totally complex motion, but it is in the motion where the 2 parts move relative to each other, and one of them is kind of structured in an interesting way. And lastly, it does not, and it lacks mirror symmetry. We'll get to this in a second. If I had tried to build this and just made that, well, if I'd done something where I tapped this and there was no lack of reflectional symmetry, this wouldn't work. And I'll prove that to you. But importantly, this doesn't have any magnets. Right? That would be cheating if I put a permanent magnet in there and say, it generates a magnetic field. It doesn't have any batteries. Right? There's nothing driving this current. It doesn't have any net charge. This is a big misunderstanding. People who don't work on this, a lot of you work on plasma physics, so you're used to the idea that we have moving charges, but nothing has a net charge. So people who think, oh, the Earth's magnetic field comes about because the Earth has a charge and it's spinning. That's not true. The Earth doesn't have a charge. Nor does this have a charge. Okay, so let's look into this. How is this going to work? Well, let's just start out with some basic physics. When we have a moving conductor, well, nothing's going to happen. So here's the weird thing. We have to pull ourselves up by our bootstraps. We have to say, okay, what if there was a magnetic field, but it was very weak? But anyway, the moving conductor is moving through a magnetic field. If you remember back to some early physics, freshman, sophomore year, that gives you a motional EMF, an electric field. The electric field is V cross B. So you use the right-hand rule, and you figure out that there's an electric field that goes from the axle to the rim. Okay? Just from moving the conductor, no charges, just a conductor, through a magnetic field. Before we do any math, let me just complete the story. Of course, I've put a wire between the rim and the axle, and so this electric field is going to drive a current. And that current is going to go from the rim back to the axle and up. Okay? Have an electric field, have an EMF. It looks like a battery, but it's not a battery. And so it creates that current, and that current is oriented in such a way that it generates a magnetic field upward. I started with a magnetic field upward. What that did is create a new magnetic field, made the magnetic field stronger. And so what's that going to do to the current? I have a stronger magnetic field. I get a stronger current, which makes even more magnetic field, which makes even more current, and the whole thing just runs away. And so I can start with an arbitrarily weak magnetic field to start with, and this thing will just basically generate a magnetic field we'll start discussing how strong a magnetic field it really can generate, but pretty as strong as it can. Okay? So that's the story. Yeah? Yeah. It creates a magnetic field in the same direction as B, as the red one's here. So it amplifies that. So the motion drives a current which amplifies the field, which creates a stronger current, which creates a stronger field. We'll see how this works mathematically, because the first thing I'm going to want to do is figure out, okay, how much voltage is there from the rim to the axle? Right, so I'm going to calculate the voltage, which is integrating the electric field over the distance. That is the electric field, which is V times B. I'm not doing any of the vector algebra here. It's just the product V times B integrated 0 to L, 0 to L dr. Now I'm going to put in the fact that it's rotating, so I know V is actually R times omega. Omega is the rate I'm spinning at. And so now I just have to integrate r dr, which of course is 1/2 r squared. I'm going to say that that's actually 1/2 pi times the area times the magnetic field, which is the flux. So to put this back in electromagnetic terms, the voltage in the disk is basically 1/2 pi, the rate, angular velocity I'm spinning the disk at, times the flux in magnetic field going through the disk. Does everyone see that? Just a little bit of algebra here. This shows me how much voltage I have. Now I'm going to look at this as a circuit, right? Voltage is equal to IR. It's actually not voltage, it's EMFs, but this is the way we all did circuits. IR is equal to the EMFs. We have this EMF that I just calculated. That's what you'd call the motional EMF. That's due to my movement. And then we have what you remember from an inductor. We have the back EMF. It's a circuit, so it has a self-inductance, L. And the back EMF is minus L times the rate of change of that current. Everyone remember that part from E&M? And they probably stopped. I teach this stuff to freshmen, and I've learned I can no longer appeal to the workings of a car's alternator because cars don't have alternators anymore. But this used to be the way to illustrate how much voltage you could get out of these. You could generate sparks in your spark plug using the back EMF. Okay, but so it's a real thing. It's a real thing. So there's our circuit. Now I'm going to say, well, the flux through the disk is actually the current times a mutual inductance. Okay, and the mutual inductance is just the proportionality from the current through this loop times this circle. Sort of that, the amount of flux through from here to here. So do we all remember mutual inductances? There's self-inductance, mutual inductance. M is the mutual inductance. So now I've got an equation that just involves I and di dt and a couple of things, including my rate of spinning this disk. And I collect them all into a nice differential equation. Di dt is this product of this stuff times I. Okay? So this is just basic circuit pieces. But you'll see now that my motion is giving me a positive term here. This is the generation piece. Okay? The faster I spin, the more it generates. And the resistance of the disk is a dissipation piece. And these two are battling. And this is a nice differential equation. I know how to solve it. All this stuff is constant. So di dt is a constant times I. And the solution is exponential. Yeah. What is what? M is the mutual inductance. It's the mutual inductance of the wire to the disk. How much flux, how much the current in the wire generates flux in the disk. Okay, it's just a, geometrical constant, really. So it's an exponential. We get I going as whatever the initial current was, e to the gamma t. So no matter how small I start that initial current or that initial magnetic field, this thing is going to grow exponentially until something happens. We'll discuss what that is. And you now see that we will get growth provided I spin this thing faster than this factor here, 2 pi r over m. 2 pi times the resistance divided by the mutual inductance. Okay, so what does that mean in terms of my speed here? Well, if I spin at a certain speed v, then omega is v over L, let's say the radius of the disk. I have r for resistance. The resistance is 1 over the conductivity times the length. Okay? And the mutual inductance, here's a secret. They may not have told you in basic physics, but it's true. Inductance, mutual inductance, self-inductance, it's geometrical and it's about length. So I think I warned Nick. I was going to ask him what his self-inductance was. What's your self-inductance, Nick? Okay. that the inductance, your inductance is just your size times mu naught, which is a universal constant. Okay. Call it a meter, right?
All right.
I don't want to change you, but just to make math easy. And mu naught is?
So 4 pi times
10 to the minus 7. We'll call 4 pi 10, so it's basically a microhenry per meter. Nick is a meter, Nick is a microhenry. Sorry, Nick. He's one macro Nick, but also a microhenry. Yeah, so inductance, see, people get a little freaked out about it. I don't know why. It's taught in a really bad way, I guess. It's just about the size, about your size. So this mutual inductance is nothing more than mu naught times the length of this thing. So there we have it. I need V over L to be bigger than this. I need this product in the denominator, mu naught sigma L V, I'll put them all over here, to be bigger than 2 pi. As promised, this is the magnetic Reynolds number. I told you it was the conductivity, the size, the velocity. I didn't tell you mu naught was hiding in there. That's just a universal constant that makes this dimensionless. Have no dimensions, it's just 1 or 10 to the minus 6 or 10 to the 10 or something like that. So as long as I spin fast enough that this is bigger than 2 pi, my current grows exponentially. Everyone cool with that? Question? No, this is not a collisional. This is not a collision length. This is the conductivity. So if you were given a block of material, the resistance is the area. It's the length divided by the area divided by the conductivity. And I basically said, well, area is just length squared. So I'm doing twiddly math here. Okay? So in the end, whether I can spin this thing fast enough all depends on whether I can make this product bigger than 2 pi. This is the third ingredient. So we have all those ingredients. If I don't spin it fast enough, now I want to make a couple of observations about this toy. If I were to start with a magnetic field that goes down, what happens? Well, if the magnetic field goes down, then V cross B goes from the rim to the axle, and it drives the current in the opposite direction. And what happens to the magnetic field from that current? It's also going down. So it will exponentially grow as well. Of course, we all knew that about the exponential growth solution. Oops. Backwards here. If I0 is negative, it grows exponentially. Changing the sign of the factor in front doesn't change the fact that it grows exponentially. So our dynamo, this thing here, can operate in 2 modes. It can amplify magnetic field if it finds it upwards or downwards. Either way, you get a magnetic field that grows exponentially. Okay. 2 modes of operation. However, if I reverse the direction and flip the thing over in a mirror, I'll let you do this at home, it will also grow. As long as I do both of those things, reflect the whole thing in a mirror so it looks like this, and I spin it in the other direction, then, right, V cross B is V cross B. It's actually going, in this case, from the rim to the poles, and then that will amplify it. But if I do one and not both of those, I reflect it in the mirror but keep spinning it in the same direction, or I spin it in the opposite direction, I do not get exponential growth. So this is that last bit about the reflectional symmetry or rotation is important in some sense for dynamos. And here it clearly is. The dynamo only works in one direction. And the last thing I want to get to is, I've talked about exponential growth. We all know that doesn't work forever. Right? Something has to give. Does anyone have any insight? If I built this toy and I tried myself to turn this thing, and I could turn it fast enough, and I kept turning it at that one speed, and the current would just get larger and larger and larger, what would go wrong? When would I run out? When would this whole process not be exponential? Yeah. Okay, you're right. You're right. So I might have problems with the wires. Maybe I could solve that. Maybe. Yeah. With some force. And so the current is going to start making that force bigger and bigger and bigger, right? The current, excellent. A current driven through a magnetic field involves a force. And actually, since it's through this kind of magnetic field, it involves a torque. And I'm going to be doing my driving against the torque. And as the current gets exponentially larger, the torque will get exponentially larger. And I'll show you that. And that means I have to do exponentially increasing, I have to supply an exponentially increasing power. That I guarantee you, no matter how good the wires are, I am not capable of supplying anything with an infinite amount of power. So I will run out of power and basically will be stopped. So that's the force, I cross B. So it is in, if you do that, you'll find the force goes backwards against the velocity. That seems natural. The torque is F times R. I do out all this, and I find that the torque is the current times the flux in the disk. Looks very similar to the expression for the IMF. And it's, if I put in my mutual inductance, the torque is the mutual inductance times I squared. So no matter which way the current is flowing, I have to exert a positive torque to overcome that negative torque. The power to rotate anything is the angular velocity times the torque. That's the power it takes me to drive this. And so that is omega m I squared. Okay? And if you subtract off, there's power that gets dissipated by the resistance in a current, in a circuit. We all remember it's I squared R. That's the power dissipated. So that power is lost to heat. So I take the power I inject, subtract off that loss to heat, and I get this expression here, which is gamma L I squared. So where is that power that's not dissipated in heat going? What's happening to it? Yeah. Right. You recognize Li squared is the energy stored in the magnetic field. Actually, 1/2 Lr squared is the energy stored in the magnetic field. So because I have it exponentially growing, so this is 1/2, this is the derivative of 1/2 Li squared. So over time, all the energy that I've supplied that didn't get dissipated as heat has gone into building up a stronger and stronger magnetic field. But eventually, I'm going to run out of oomph. And so my rotation rate is going to start dropping because I don't have enough force to overcome that exponentially growing torque. And so I will drop down to the critical rotation rate where I only overcome the ohmic dissipation. So all my work is going into heat. No more magnetic field is being built up. I have as strong a magnetic field as I am physically capable of building, and that means the current saturates. So this is the way dynamos ultimately work. They basically generate a magnetic field through their motions, through a magnetic field, having an electrical conductor that's using the motional EMF to drive the currents. And then once the thing that's driving the motion is sufficiently taxed by the back EMF, by the back force, it runs out of juice. Okay? So that's the toy model. Let's think about reality now. Many of you have mentioned that you're familiar with the equations of magnetohydrodynamics. These are they. I have a continuity equation for mass density of the fluid. I have a momentum equation for the velocity of the fluid. And I have an energy equation for basically the temperature of the fluid. I don't want to dwell on all the details here, but I do want to point out that in this momentum equation, I have the kinds of forces you expect in a fluid, the pressure gradient. I have gravity. This is viscosity, if you haven't seen it. And then I have J cross B. Because it's a conducting fluid and there's current flowing through it, there's a force due to J cross B. That's the same force we used in our toy model. That appears in MHD. It's very important. And there's also the dissipation of energy through the ohmic dissipation. 1 over the conductivity times the energy density squared. That's heating up the fluid. These two things are very important. And they are the places that the magnetic field has an effect on the flow of the fluid. Okay? Lastly, in MHD, we have a combination of Faraday's law and Ohm's law. This tells me how the magnetic field responds to the conducting fluid. Okay? And I don't want to dwell on this either. Ohm's law, or Faraday's law, as we all know, is partial derivative of B is minus curl of E. Right? That minus sign is Lenz's law. That tells us it's going to oppose the change in magnetic field. And then I put in what the electric field is in this conducting fluid. It's V cross B, as we discussed. And then it's also the ohmic 1 over sigma times J. I put that in. And basically, I get out that d by dt has to be a to b squared. Importantly, we have a way that the fluid is controlling the magnetic field. This is our motional EMF. This piece here, the V cross B, remember, was so important in the toy model. That's what generates the current. And then this is what opposes the motion. The current actually can oppose the motion. So this is what goes into all these models. And you'll be hearing by real specialists who solve these. But I just want to point out that these have all the same ingredients as our model. And there's a nice limit that we can think of. If we're not familiar with MHD, but we've lived on a planet with an atmosphere, which I think you all have, then you're familiar with how fluids behave. Okay? This is different because it has a magnetic field and a current. But if the magnetic field is weak, then those go away. And we basically have regular old hydrodynamics that we all grew up with. We're all familiar how fluids flow, how you pour beer into a glass, right? We all know that. So here are the equations for that. And we can basically solve those without worrying about magnetic fields. And then, right, so we solve those first. And then once we've done it, we know what V is. Now we turn to this weird thing. And now I've used a little bit of vector calculus to rewrite the curl of a cross product. Probably all remember your tables of vector calculus. And I've rewritten it this way. It ends up being a v dot del B term, a b dot del V term, a b div V term, and there's a fourth one, which would be v div B. But I throw that away because div B is equal to 0. We have this what looks like an even more complicated term here. But the important thing is, if we've solved the fluid part, we know how this thing's flowing. And we know it's a good conductor. Well, we'll find out, because eta is the resistivity, 1 over the conductivity. Then V is known, and this equation is linear in B. It's just an equation for what the magnetic field does if I can generate, if the flow doesn't care about the magnetic field. It's known as a kinematic dynamo. Okay? So it's linear, and basically I treat V as a known. And here's the magic part. This piece here that came out of the vector calculus is really just the time derivative of the magnetic field. If I'm flowing along with the fluid, I see the magnetic field changing. This is, the left-hand side is just that term. How does the magnetic field change in time? This term here looks a lot more complicated, but I can see there are no derivatives of B. Right? It's just the vector B times some thing. The thing happens to be a second-rank tensor. Okay, so what? And it involves derivatives of the velocity field, but not of B. So really, I just have the time derivative of B is B times the matrix. Okay. Now I can ask the same question. What's going to happen to B? Is B going to grow? Well, really, the answer is if this matrix has a positive eigenvalue, yes, B is going to grow. Okay? Because if I multiply by that eigenvector, I'll get d by dt of b is gamma times b. And we've already seen in the toy model, if gamma is positive, exponential growth. This is just a vector version of the same thing. So we get growth. Now, this is gamma. It's actually, I've worked out, this is just gradient of, this is just this term here, which is all gradients of v, which is just basically v over whatever the scale of this thing is. And then I have this, which is the dissipation term. It's eta times del squared b, which means eta over L squared. And of course, del squared is always negative. It always leads to diffusion. So gamma is just that. It's just v over L, 1 minus eta over LV. Okay? So no matter how complicated this fluid is, in the end, I'm going to get exponential growth, provided I have this growth, provided my eigenvalue is positive, and this combination LV over eta, which is really mu naught LV sigma, is greater than 1. That same lesson we got from the toy, except it used to be 2 pi. Well, this is all sort of twiddly math, right? I just said this is sort of what it is. So we don't know if it's 1 or 2 pi. But at any rate, this magnetic Reynolds number has to be big to make things grow. And yeah, a couple of other things. If I reverse the sign of B, right, I have an eigenvector. Well, minus that vector is also an eigenvector. We all remember that. So I also get exponential growth. So my magnetic field generator will work in 2 directions, 2 modes. If I reverse the sign of the velocity, well then, I imagine I could actually change the sign of my eigenvalue. But if I also reflect space, I'll change it back again. So this dynamo will also do that. If I both reflect in a mirror, invert space, and change the sign of the velocity, I have a working dynamo again. If I do one and not the other, what I know is what used to be a positive eigenvalue has become a negative eigenvalue. Okay? That doesn't mean there wasn't a negative eigenvalue that becomes a positive one, but I do know that that one particular direction is no longer an amplifying direction. So just like the toy, MHD has all the same properties built into its dynamos. And I just want to illustrate one flow that will do this. And it's a very simple flow. Basically, V is some constant x hat minus y hat. So that's basically fluid that's converging to the x-axis and diverging away from the y-axis. Right? If I have that kind of flow, well, let me work out my matrix here. That was just the derivative of Vx with respect to x, etc. And I basically get a 1 and a minus 1 on the axis, on the diagonal. So do I have a positive eigenvalue? That was the only thing I needed to make this work. Yeah, right? B over L is the eigenvalue. So this flow will create a strengthening magnetic field. And if you're used to doing MHD by cartoon, that's how I am. What happens is if I have this, the positive eigenvalue is in the x direction. So if I have a magnetic field that's only in the x direction, then this flow is going to take those magnetic field lines and move them towards the x-axis. And it's also going to stretch them out. That was the ingredient we talked about. I need to have that positive eigenvalue. I need to have a flow that's going to stretch. And it stretches in the x direction. It doesn't stretch in the y direction. That's a decaying eigenvalue, which is not what we're after. And actually, it's not just magnetic fields, but you can imagine any little region of space. If I put in a little circular drop of dye and put it into this flow, then that dye, which was a circle, is going to get stretched into an ellipse, and then a longer ellipse, and a longer ellipse, right? So there's one direction in this drop of dye that's being extended. It turns out that's the eigenvalue I'm after. If you do dynamical systems, this is what's known as a Lyapunov exponent. Okay? But it basically says if I have a flow where if I put in a drop of dye, imagine a spherical, three-dimensional flow, I'd put in a spherical drop of dye. If my flow stretches that dye into a long, thin strand, I have a flow with a positive eigenvalue. I have the possibility of a dynamo. And guess what kind of flows will stretch out little blobs? You put your cream into your coffee, right? You need turbulent flow, right? Yeah, that's what you do to work the cream into the coffee, because if you just let it sit there, it takes a long time before it fills up your coffee. But if you stir it with a spoon, you create a little turbulent flow, and it takes that spherical drop and stretches it so fine, you don't even see the difference. It looks like it's filled your coffee. Right? That's all you need, turbulent flows. They always have this positive Lyapunov exponent. And so our turbulence, yeah. Can we do what? No, that was not turbulence. You can get a positive Lyapunov exponent without turbulence, but turbulence will give you a Lyapunov exponent. So it's sufficient but not necessary to have turbulence. Nature always does it with turbulence for some reason. So turbulence always has this property of stretching things. Okay, so we're always in a regime where we can amplify magnetic fields. However, how do I get turbulence? It turns out you need some sort of driving. So you need something that basically wants, and it could be your spoon in the coffee. In astrophysical systems, there aren't a lot of spoons out there. So it tends to be heat trying to get from one place to another will actually drive an overturning kinds of turbulence. But you also need the viscosity to be small enough that it doesn't dissipate that turbulence, doesn't keep the turbulence from forming. So there's a second dimensional number we hear about. It's called the regular Reynolds number, the Reynolds number. It looks the same as the magnetic Reynolds number, only it has size velocity divided by kinematic viscosity. Instead of resistivity, you have kinematic viscosity. It's also dimensionless. If this is much, much bigger than 1, then your flow will probably become turbulent. And if your flow becomes turbulent, it will amplify the magnetic field. Finally, rotation is sort of important in helping generate a large-scale magnetic field, but you have to wonder, well, how fast do I need to rotate? And there's a simple answer. You need to rotate fast enough so that the turbulent flows know they're in a rotating system. Or if you like just constructing dimensional numbers, dimensionless numbers that start with R, there's a fancy word called the Rossby number, which is V over L times your rotation rate omega. And this is defined sort of upside down. So in order for the rotation to really matter, omega has to be big compared to this other ratio. And so this is, for instance, why on the Earth, where we have our atmosphere flowing around, if it flows very slowly compared to 1 day, the rotation will matter. And so, for instance, hurricanes in the northern hemisphere always rotate in one direction because they rotate once every couple of days, and in a couple of days, they know they're on a rotating reference frame. On the other hand, we'll sometimes hear that toilet bowls flush one way in the northern hemisphere. Have anyone heard that? Other way in the southern hemisphere? What? Yeah. Why is it a lie? Not fast enough. Or, yeah, usually, if you have a toilet bowl that takes more than 24 hours to flush, you should call a plumber, right? So less than 24 hours, it doesn't know the Earth is rotating. How would it know which hemisphere it's in? Okay? The Rossby number for a properly functioning toilet bowl is much, much bigger than 1. It is not affected by the rotation of the Earth. A hurricane is because it rotates very slowly. Compared to 24 hours, it takes days to get all the way around the hurricane. Okay, so these are the 3 dimensionless numbers: the magnetic Reynolds number, the Reynolds number, and the Rossby number. Now let's think about things in our heliophysics system that we're interested in. For instance, the sun. And here I've quoted things for the convection zone. Turns out the resistivity, the inverse of the conductivity, is 1 meter squared per second. Also the same if you look at the liquid part of the Earth's core. Right? Same resistivity. The velocity for the stuff inside the convection zone is actually not that fast, not that slow, not that fast. It's like a centimeter per second. Right? It's not moving all that fast. So I'm actually thinking maybe I'm not going to get a dynamo. But then I look at the length scale we're talking about, and it's 10 to the 8. 100 megameters, the size of the... So when I multiply those all together, I get my magnetic Reynolds number that is 10 to the 8. Much bigger than 1. This guy's going to be a great dynamo. Is this flow actually turbulent? Well, I can look at the viscosity, which I haven't put up here. But, oh, there's the viscosity. Sorry, this is the velocity, 1 meter per second. The viscosity. We get 10 to the 10. So the convection zone, as the name implies, is full of turbulent fluid flow at about 1 meter per second. Okay? And the rotation rate, well, it rotates about once per month. So the Rossby number of the solar convection zone is about 10 to the minus 2. That is much, much less than 1. So rotation is dominating the convections, the flows in the convection zone. So it will organize this turbulent flow to create a magnetic field. And lo and behold, the sun does have a magnetic field. Earth story is very similar. The numbers are very different. The magnetic Reynolds number is only 100. This is basically a marginally effective dynamo. Marginally, but it works. Right? Wouldn't be my choice for a dynamo, but it's what we got. The Reynolds number, though, is 10 to the 7. Its viscosity is much, much lower. It's smaller. The Earth is smaller than the sun. The velocity is much, much lower. But it's enough to give us a reasonable Reynolds number. The thing is, because the velocity is so slow, the turnover time for the stuff flowing in the liquid molten core is a long, long time. And therefore, the Rossby number is 10 to the minus 6. The Earth's core is dominated by this once per day rotation that we're all familiar with. To the stuff in there, it's way slower than a toilet bowl. It's taking literally years, thousands of years to turn over. Okay, so those are our culprits there. And let's just finish up with sort of a review then. So we have all of these ingredients that we thought we would need to get dynamos in each of these places. We have our electrically conducting fluid. We have complex motions because we have high Reynolds numbers. We therefore have turbulence. We have a generation of the turbulence through, and I'll go through the details, why in each of these cases there is a reason for this flow to become turbulent, but its Reynolds number is high enough for it to become turbulent. And finally, we've looked at the magnetic Reynolds number. It's large in all those cases. So we have what we need for dynamos. When we come back, I'm going to suggest we take a sort of 5-minute break. Come back, and we'll sort of zoom through some of these examples of real dynamos in our heliophysical system. Okay. The Coriolis effect is basically the Rossby number is the ratio of the sort of inertial effect to the Coriolis. All these numbers are dimensionless. When you talk about the Coriolis effect, that's, say, a force. So you need to take the ratio of two forces, but it's the ratio of one force to the Coriolis force. If the Rossby number is small, the Coriolis force is bigger than all the other forces, so it dominates. That's why you end up with rotation that's dominant. That's one way of saying it. Another way, it's a ratio of two timescales. The sort of rotation timescale of your body. Right.
right? So the bigger number is
No. It's meaning the magnetic field is small, slow. It is slow. So it's not being diffused. That's right. That has to do with the force. out there. Wanted to, you guys can hear me? Let's start back up. And no, we don't want to do that. All right, so that was a bit basic at a low level, but I wanted us all to understand that this idea of magnetic fields coming from these things is not some magic, right? It all follows from basic physics. And the principles are not super difficult to understand. But now we've set out the principles, let's actually get into some real applications. For instance, the Earth's magnetic field, which is not something I study, but here's a cartoon version of the Earth. We have a mantle here, which is solid, mostly. Here we have a couple cool things like subduction plates. We have big upwelling of lava. Maybe this is Hawaii, or a big hot spot under it. If this were land, this would be basically where I live, on top of the world's largest supervolcano, Yellowstone. Down here, though, is the core that's liquid. Okay? We have a core that is iron and about 10% of lighter elements. And we have a solid core that has solidified out of this, which is iron plus some smaller number of lighter elements. And this is the driving for the turbulence. That core, that solidification process is constantly happening. So we're constantly generating fluid, which is an even higher concentration of light elements because it's left behind its light elements when it's solidified. So that creates light stuff down at the bottom, which has heavy stuff on top of it, and it just wants to swirl around. Right? This is how you make turbulence. You put, okay. So there's the fluid. It's electrically conducting. There's the reason it's turbulent. We calculated the magnetic Reynolds number. So there's going to be a dynamo going on in there. That's the lesson of the first 45 minutes. So what? Well, in the outer mantle here, there is no dynamo. Probably there are no currents. So here's the interesting thing. I can take my Ampere's law. Curl of B is mu naught J. But if there's no currents, then curl of B is 0. Then I can, if B has no curl, I can write it as the gradient of a scalar. Okay, that's what you usually do with electric fields, which don't have any curl. But here I'm going to do it with a magnetic field. But I still need div B to equal 0. So chi is what we call a harmonic function. Del squared chi is 0. Graduate school, I teach E&M out of Jackson. We spend a lot of time learning how to solve this equation. Del squared chi is equal to 0. And we spend some amount of time solving it in spherical geometry. And what do we get? A solution in terms of YLMs, right? Spherical harmonics. So this is to say, when I'm outside of this dynamo, I can write the Earth's magnetic field as an expansion in spherical harmonics with radial dependence that goes as 1 over r to the L plus 1. Bringing back any memories. And so the radial magnetic field is the gradient of this. The important thing is L goes from, well, realistically it goes from 1 to infinity, because 0 would be a monopole term. And assuming there is no magnetic monopoles inside the sun, the L equals inside the Earth, the L equals 0 term is gone. So we sum this from 1 to infinity, but every higher power of L falls off as I go out from the core mantle boundary, falls off as a higher power of radius. Okay? So by the time you get up to the beach here in Hawaii, you're not going to see a lot of the higher L harmonics. Okay? They are kind of died away. And I'm not going to go through, I had a sort of review. Oh, by the way, I should tell you, these lecture notes and this lecture are all going to be online. So you can look over these lecture notes. If you don't remember much about spherical harmonics, I don't think it's all that important, except to remember that the higher the L is, the more waves there are. So L equals 1 is the dipole. Basically, it's positive in one hemisphere, negative in the other. L equals 2 is the quadrupole. Positive in both hemispheres, negative around the equator, or vice versa. That's the basic premise. When you get to L equals 5, you basically have positive, negative, positive, negative, positive. It changes 5 times. It has 5 different poles to it. I don't even know the name for that. Okay, what about the Earth's magnetic field? This dynamo is going to generate a magnetic field. This whole story made it sound like it was going to generate a very complicated magnetic field. And yet, we think of it as a big dipole. But if I look at a measure of how strong each L value is, I get about the same number. L equals 2, L equals 1, which is the dipole, is a little bit stronger, but not much. They're all about the same strength. Why? Because it's turbulence. Right? It's doing the messiest thing it possibly can. Why would turbulence make a big, strong dipolar magnetic field? It doesn't. However, if you saw me point to this red line here, this is actually the spherical harmonics if I measured them at the core mantle boundary, right, where the currents are, right, where the magnetic field is being generated. We don't live there. We live up here. So I need to take my expansion, which falls off as 1 over r to the L plus 2, and evaluate it here. And so the dipole term falls off slower than the quadrupole term, which falls off slower than the octupole term, etc. So we see at the Earth's surface a magnetic field that's primarily dipolar. That is not because the Earth generates a dipolar magnetic field. That is because we live where the Earth's magnetic field has become so simplified that the dipole moment is all that we see. Here, in fact, is a map of the Earth's magnetic field. Red is magnetic field coming out of the BR as positive. Blue, it's negative. Pretty nasty, right? There's negative pieces here over the South Atlantic. There's big positive pieces. Yeah, you get to see negative pieces down here and down there. It's pretty nasty. The reason it looks so nasty is I'm plotting it at the core mantle boundary. And in fact, up here, I give you a little guide. This is the Earth this is the mantle in the light gray, the core in the dark gray. And that solid black line is where I've made this map. So if I let this map, if I basically take that out, play that again, you'll see that black circle gets bigger. So I'm looking at different places, and the magnetic field gets simpler. That's simply because all of those higher order multipoles are falling off so fast with radius that they start to become less and less important. And by the time you get up to here, which is actually a quarter of an Earth's radius above the surface, we see a lot of magnetic field coming out of the positive magnetic field in the southern hemisphere and negative magnetic field in the northern hemisphere. The magnetic field looks like a big dipole. All right. The other thing that this should convince you of is, well, if it's all this turbulence that's generating the currents that's making this magnetic field, and the turbulence is swirling around, then probably the magnetic field is not staying fixed. It's going to change in time. And lo and behold, it does change in time. Year 1900, plotted at the surface. Over the course of time, 2010, I don't have any coefficients for 2020 yet. The magnetic field changes. That wasn't all that exciting. Here's what it looks like at the core mantle boundary. This is the magnetic field right close to where it's being generated. And we said we actually knew the equation for the generation. It was this bad boy, which is basically a combination of Faraday's law and Ohm's law. So this tells me about the change of magnetic field due to the velocity. Now, when I was trying to convince you that a turbulent velocity would amplify this magnetic field, I said, imagine we knew V ahead of time, because it was just due to overturning turbulence. We could play this game backwards and say, well, say I measured B, which we have, but I learn what V is. And yes, you can. You have to make a few approximations, but since we've measured the magnetic field for 100 years, if we assume that the flow down there, it's really slow, is subsonic, then it's probably about incompressible. So div V is equal to 0, so I can get rid of one of those terms. I'll also ignore the diffusion part. That just makes things messier. And lo and behold, I just have this equation here, which is just a continuity equation for BR. So what, in this approximation, what is happening to make this magnetic field change is the Earth's core flow is moving it around. And we've measured the magnetic field changes, so we can measure the flow, and that's what's plotted here. And this comes out of one of the chapters of your textbook. And so you can see this is the flow field that is moving our magnetic field around. It's mostly going sort of east to west, flowing up along the Caribbean here, big vortex over the northern hemisphere. It's all pretty slow. Sort of see, there's the inversion. I think we see, you look at these numbers, basically it's going to go about 1,000 kilometers in a century. But that is, for instance, what has carried a region of fairly weak magnetic field, basically made a magnetic field that had a reversal in it, moved it up into the South Atlantic there, and created what's known as the South Atlantic anomaly. Anyone who works with Earth orbiting spacecraft will probably have heard of this. It's just a part of the magnetic field that's particularly weak. Therefore, our radiation belts are particularly low down, and our satellites get tangled up in them. A lot of good data from that. But that's just the evolution of the magnetic field. Wait around another couple hundred years, and that will have moved off to a different part of the Earth. But so there you have it. Our Earth is generating its magnetic field, and the magnetic field is changing. One other thing we want to look at is what happens over longer periods of time. We've only been measuring the magnetic field for a century, so we really can't play this game for much longer. However, we've had volcanoes for a lot longer than that, and they have this liquid iron that is nice fluid. It's not magnetized, but then it solidifies in the presence of a magnetic field, and it gets magnetized, just like nails get magnetized in a magnetic field. So if you look at the lava in a volcano, in a volcanic flow, you live in Yellowstone, you have lots of volcanic flows to look around and see. You look at any of those, they will record the magnetic field from whenever they solidified. So by going to volcanic lava from different periods of time, you can figure out which orientation the magnetic field was in, and this is the result. Basically, we see bands of black and white going back millions of years, 5 million, 10 million, 15 million, 120 million years. I don't know too much more about this signal than this, but what's black is the magnetic field we now see, what we call a normal magnetic field. The dipolar component goes from south to north, like we saw on that big map. Remember, that's just the L equals 1 term in an expansion with an infinite number of terms. I've really left out a lot of information when I tell you about the dipole field. Remember, the Earth's magnetic field is not a dipole. It just has one term that's a dipole. But that's all that the volcanoes really see. And if you go back far enough, it will actually have been in the opposite orientation. And then before that, the normal, reversed, normal, reversed. Just like our toy dynamo, the Earth's magnetic field seems to prefer its dipole to be in one of two orientations. But it seems to flip between them, at random, more or less. If you take those MHD equations very seriously, and this is one of the better simulations by Gary Glatzmeyer, got his start here at HAO working with Peter Gilman, studying the dynamo of the sun. He went on and started doing the same thing to the Earth. This is his rendering of a dynamo operating inside the Earth. This region here, he doesn't show you, this is the liquid core. Out here, where everything goes straight out, this is the mantle. And the magnetic field goes outward because there's no current, and it's basically the gradient of a scalar. Okay, so you see the field lines going out the south and coming back around to the north. That's the dipole component. But when you look at this field, is this going north to south? No. The dynamo is really not generating a north-south magnetic field. It's generating an east-west magnetic field, which is what it should, because the Earth is rotating east-west. That's the direction it's stretching all these fields out. So, but there's also no gradient of a scalar that's going to give you something that goes east-west. So that east-west field, which is the dominant magnetic field of the Earth, is stuck inside the Earth. We don't get to see it. We live out here, where the only thing we see are the multipole terms that expand from them. Okay? But what we think, based on this, is the dynamo will generate east-west magnetic fields mostly, and a little bit of north-south. Those form the dipoles. Probably should, I'll give a quick overview of how this applies to some other planets. Mercury, Venus, Earth, etc., Neptune. And we see that there are a lot of dynamos. Venus, Mars, notably don't have dynamos. The moon doesn't have a dynamo. Based on the story I just told you, the moon, that makes sense. It's basically a rock. There's no moving conductor. Why would it generate a magnetic field? Venus actually does have a liquid core, but it doesn't have a dynamo. What's it missing? Probably missing the turbulence. It doesn't have any volcanoes on it. I mean, it's not a happy place to live, but one thing you don't worry about when you're on Venus is volcanic eruptions. Speaking as one who lives on the Earth's largest supervolcano, that'd be a big load off my mind, but I'm not that worried about it. So yeah, it doesn't have the turbulence, no magnetic field. Mars, pretty similar story. It may actually be mostly solid all the way through anyway. So in the past, it probably had the ingredients. Jupiter, Saturn, yes. Some of you are studying these magnetic fields in these places. Here are some of the pictures of those. Saturn is a impressively dipolar magnetic field. Quadrupoles must have died off pretty far down. I don't really sort of linger too long on the basics, so let me just finish up by pointing out our one story about the saturation was that we need the driver of the turbulence to be sort of, it's going to determine how strong the magnetic field will get. The magnetic field will get exponentially strong until it creates a force that feeds back and prevents the turbulence from doing its stuff, and then the turbulence will get weaker and the magnetic field will sort of be at that level. So if, and this is the version that they go through in the textbooks that explain how you can calculate how strong the turbulence is in each of these bodies and how strong the dipole magnetic field is in each of these bodies. And you do get this nice scaling. Now there are some error bars here. We don't really know as much as we would like to know about the way heat is being generated and transported in Jupiter or Saturn. Saturn particularly, they're kind of guessing for that. But if they make the right guesses, they can say yes. So stronger magnetic fields come from things where the turbulence is being driven more strongly, like Jupiter. That's why it has such a strong magnetic field. Not because it's big, but because it actually has strong turbulent generation, and that actually can overcome the back reaction, the torques being provided. Okay. Sorry, this is going a little fast, but sort of gives you an overview. We have this dynamo operating in all these planets. I only study the sun, so I want to get to that as well. Story is very similar. We have this ionized plasma, really good conductor. The outer portion, the outer 1/3, is in turbulent convection due to the fact that the heat being generated at the core is sort of being transported out by radiation until it gets to that level. And the radiation kind of becomes ineffective, and turbulence takes over. It creates this convective envelope in the outer portion of the star. Okay? As I said, the Reynolds number for this turbulence is 10 to the 10, really big. Okay? Good turbulence. The magnetic Reynolds number is 10 to the 8, very good. The Rossby number, not so great. So this turbulence is very fast, and so a 1-month rotation period can appear kind of slow. It turns out some of this turbulence is turning over deep down slower than that. So we do have a Rossby number of about 10 to the minus 2. Here's the magnetic field we see. Those of you who don't know, the sunspots that we've been observing for a long time are the manifestation of the magnetic fields. And actually, when you measure it in Zeeman splitting, you can actually see that where there's a couple of sunspots, there's a region of magnetic field into the sun and then out of the sun. Negative and positive. Over here, positive and negative. Positive, negative, positive, negative. So the sun is generating a magnetic field just like the Earth is, except it's a lot more complicated. Well, wait, I told you the Earth's magnetic field is wicked complicated too. It's just if you live far away from it, it looks simple. But this is not necessarily any more complicated. However, there's another thing that's puzzling about it. If you look here, the magnetic field seems to go from the right to the left. In solar physics, this is the west and that's the east, so it's going west to east. And then up here, it's going east to west. So the sun's magnetic field is east-west, not north-south like the Earth's magnetic field, right? What did I say about the Earth's magnetic field? Mostly east-west. Same thing, right? So really, you know, this is not all that different. I can take this map of the magnetic field, sort of stretch it out. So we're going to see a few plots like this. These are 360 degrees of longitude. This is 90 degrees of latitude. You'll see plus, minus, plus, minus, plus, minus. Positive, negative, positive, negative. If I do this and I throw out some of the spherical harmonics, I will have a map of the sun's magnetic field this way. I could do the same for the Earth's magnetic field. This is at the core mantle boundary. You guys can all probably see there's a difference, but it's not that big a difference. Right? We've got dynamos. They generate magnetic fields. There you got it. This is sort of more complicated because the Reynolds number is 10 to the 8. Here the Reynolds number is only 10 to the 2. So it's a much gooier fluid. So it's not doing as much turbulence. The other thing that's going on, the Rossby number is 10 to the minus 2. So rotation is not as effective a force in the sun's dynamo as it is in the Earth's dynamo. So those are the two big differences between those. But you can see they have a lot in common. So let's see here. We'll have, so the same trick we played with the Earth's magnetic field in the mantle, where there's no current, that is, J is equal to 0, we can play in the portion of the magnetic field of the sun that's outside of the sun's body, right? In the corona and the solar wind, the material is very sparse there. So there aren't a lot of charge carriers. The current is very small. So we could say that J is equal to 0 there. Once again, we can write B as the gradient of a scalar, and that scalar has to be harmonic. So we use spherical harmonics to expand the sun's magnetic field the same way we do for the Earth's magnetic field. Voila. So when we have our spherical harmonics, we have the power of the spherical harmonics falling off with radius. And so if I know the magnetic field at the surface of the sun, because I measure it with Zeeman splitting, then I can extrapolate it. And here it is extrapolated up to 2.5 solar radii. And the blue contours are BZ coming out, or BR, positive BR. And the green, gray contours are negative. So we see actually that it is kind of dipolar, right? The sun's magnetic field is coming out of the South Pole and going into the North Pole. And there's the place where it crosses over BR is equal to 0 right along that line, right? So does everyone see what I'm plotting here? This is the radial component of the magnetic field. It's a function of latitude, 0 to 360, and, sorry, longitude, 0 to 360, and latitude, well, I've only gone from minus 70 to 70. But this is out when I've extrapolated it out because I'm assuming there's no current outside of the sun itself. The sun has lots of currents. It's a really good conductor. It makes a magnetic field that looks like this, and then everything else gets extrapolated outward. So this is that kind of plot, and we're going to start. It looks really dipolar here. This is 1996, and actually the magnetic field is coming out of the South Pole. Sorry, coming out of the North Pole, going into the South Pole. It's blue solid contours here, but very much dipolar. And what we see over time is that it changes and then becomes really complicated, and then it's hard to read the dates as they flash by, becomes very dipolar going the other way. It's flipped. Okay? And by the end, it's completely flipped, and this is 2009. Okay? So in the course of about 13 years, it's flipped from one orientation to another. The sun's magnetic field flips like that all the time. Here is just the dipole moment of the sun. This plot is a little complicated. It's about as far as we're going to get in these lectures. But what I've plotted in green up here is the magnitude of the dipole moment. Dipole moment's a vector. It has magnitude and direction. I plotted the magnitude in green. It goes up and down and up and down and up and down. For fun, I plotted minus the magnitude down here. In the red, I plot just the z component of this vector. That is the north-south component. That has a sign. And you can see that goes from positive. Then in 1980, it flips over to negative. Then in 1990, it flips back to positive. Then in 2000, it flips back to negative. Okay? The z component of the dipole moment. Does the dipole moment go away? No, it's always got a direction. It's always got a magnitude. During these times here, it is primarily north-south or south-north. During this period here, which is solar maximum around 1990, it is smaller a little bit, fluctuating rapidly, but not zero. Probably pointing to the east or to the west. So there's a big misconception that somehow the sun's magnetic field just points up and down. The Earth's magnetic field almost certainly does the same thing. It does not shut off and turn on the other direction. It's just, after all, 3 numbers out of an infinity of numbers. Those 3 numbers all probably become a little bit smaller, and then they're big again. When we look at the time when that dipole moment is fairly small, what we see is this kind of shape here, where I have magnetic field coming out, in, out, in, out, as I go along the equator. Now, is this a dipole? This is a quadrupole, right? 1, 2, 3, 4, quadrupole. What's happened is the dipole has become weaker. The quadrupole has not changed very much, but now the dipole is not strong enough to overwhelm the quadrupole, and so we see a quadrupolar magnetic field. If you wanted to look at the place where the magnetic field, yeah, and so here's more of a dipolar magnetic field, 1995, 1997 here, right? So that's what's happening to the sun's magnetic field. It's not reversing the way people say. It's just that the dipole moment is reversing. Let's see. I think, well, so everyone's familiar with the idea that the sun has this kind of periodic behavior. as I told you, the sunspots themselves are a manifestation of this magnetic field. It's kind of, they were little specks, and we saw the magnetic field was much more dispersed than that. If we make a plot of the number of sunspots, and let's just look at this bottom plot here. This is sort of a number, a number that characterizes how much of the sun surface is covered by spots, starting in 1870 and going forward. And you can see it goes up and down. This is the solar cycle. Right. So this is the manifestation of the sun's magnetic field getting sort of one dipole moment here, positive, then negative, negative, then positive. And then these are the sunspots forming magnetic field that mostly goes east-west around the equator. And they appear when the magnetic field has a much richer multipolar form. Okay. So I don't know. I guess the thing I'll end on is that's the very brief, crude story of the sun and its magnetic field. I thought we should mention a few other stars that might have magnetic fields. You've taken any kind of astronomy class. This is the famous Hertzsprung-Russell diagram, which shows temperature along the bottom axis here, plotted backwards, as astronomers always do. So the higher temperature is over on the left, the lower temperature is on the right. And then another wonderful thing about being in a very ancient field is there's all kinds of nomenclature that doesn't make any sense anymore. These are called O stars, B stars, A stars, F stars. It's just basically progressively cooler stars. And then this is the brightness. If you go to the B stars, you will see the structure of the star. This is the radiative zone. There's a convective zone in there. But sort of the whole star is radiative outside of the center. So there's no turbulence. There's no magnetic field. Right? That's our rule. You got to have that turbulence. It might be generating a magnetic field in there, but this is such a good conductor, it'll screen it right out. The sun has a hefty region of turbulence, so it generates a magnetic field. If you go to the really cool stars, the M stars, they're all convection. Right? Lots of turbulence. And in fact, if you plot, this is the temperature done backwards, and the radius, you plot the depth of the convection zone. It's basically something that starts for very hot stars. There's no convection envelope, and then it gets bigger and bigger until it's the whole size of the star. We expect no magnetic fields there, and in fact, that's what we see. When you look at what I'm going to show up here is the stars that produce X-rays. And that's these stars. F stars and above have a magnetic field, and what we'll hear about in the afternoon is that means they're going to produce lots and lots of X-rays. Or another measure I think we heard mentioned by at least one person is the calcium spectral line tells us about how much magnetic field is on the surface. We have Dr. Ricky Egeland, who's probably now become the world expert in measuring the calcium H index and K index. Yeah. Yeah. No. If they're looking at stars, Ricky can back me up. If they tell you a star is magnetically active, probably they're looking at the calcium spectral line, seeing a particular signature of magnetic field. That's the easiest way to, I know. Everything you said would be what you'd want to know. Yeah. It's very difficult to see a CME on another star. Yeah. And they say it all the time. Yeah, so this is what they're seeing. In fact, this is called, is this right, Ricky? The HK is called the activity index. Yeah, magnetic activity index.
X-rays are also an activity.
And then there's also X-rays. We have not had the ability to measure X-rays on stars for as long as we've had the ability to measure calcium absorption in stars. Anyway, here's the F stars, F5, sort of G stars. Left of this, there's just no signature of magnetic fields. The farther right you go, stronger and stronger signatures of magnetic fields. I'm going to leave it at that. The last couple of slides go into the math of how you can explain this in terms of the numbers we've already covered, but I'll just leave that and take any other questions we have. That's right. That's right. Well, I will say this. The calcium will tell you about small-scale magnetic field because it's not a Zeeman signature. It's actually telling you mostly about the heating, which comes up in the afternoon lecture, that magnetic fields lead to heating, and that leads to this signature in calcium, which is a reversal in the spectral line. So I think a small-scale magnetic field would generate this. In fact, there are some signatures of what happens as a function of the rotation rate that people think is due to what they call basal magnetic flux. That's unstructured magnetic flux. They don't have sunspots, and they don't have convection. That's the problem. What they're really lacking is convection. They're just sitting there as far as we know. The radiation is just coming out as a form of photons all the way from very, very inside portions of them. So without that swirling, they're like big Venuses. They're hot, like Venus, and they're boring like Venus. Boring if you care only about magnetic fields. Venus is magnetically. Sorry, I couldn't. Yeah. All right, I'm turning this over to Ricky.
Yeah, it's called the Von Preston gap in nobody.
Okay, you heard it from him. Von Preston gap. Yeah, this is, the basics are here for you guys to appreciate. The details are actively being studied. This is not historical stuff. This is a pretty old graph, but this is ongoing research. Yeah. Yeah. Some people say it's a random. It's 300,000. It has a time scale.
How would you?
Good question. I guess you could do it that way, yeah. Unfortunately, the volcanic records don't actually give you strength. If you remember, you probably don't remember back to the ferromagnetism is something that just basically saturates. So you just get a direction, and it's above this strength. But
What we were talking about with
yeah.
bipolar
Right.
sort of coming and going.
Right. So from the record I showed you, which goes back into the 70s, we have multipole moments for the sun. We have multipole moments going back for the Earth for 100 years. Right. And those are made from measurements, and they make measurements at the Earth's surface and extrapolate them downward. That's one of the reasons I didn't point to the fact that multipole moments above 14, they kind of look strange. They go up. I think that's mostly an artifact of the fact that they're taking very small signal and extrapolating it. It's probably an artifact of that. But as long as because you can only measure a finite number of places on the Earth. Certainly in 1905, that was true. Yeah. Yeah, very strong magnetic activity. Well, it's got a lot of turbulence. Now, Mark Misch will be here tomorrow. he will give you a lot of details about the solar dynamo and I think stellar dynamos as well. The detailed explanation, there is some role to be played, we think, by the lower boundary of the turbulent convection zone. And you'll hear about that. So you should raise your hand and challenge him and say, M stars have no tachocline, no lower boundary, fully convective. Explain that, Einstein. Yeah. No, I'm sure people give a lot of thought to that. It is puzzling. But the story I've told you, which is, as I promised, a very superficial one, at least they have turbulence. And at least they're electrically conducting. So it sort of has the ingredients, and they're rotating, so that organizes it. The lack of a lower boundary is a sort of first-order problem that I haven't really problem. Yeah. No. If it has, it's very new, and I haven't heard much about it. I could tell you a little tidbit that was thought about for the Earth. And I believe Janet Lumen is one of the people who has played this up a bit. It is thought that maintaining an atmosphere with water vapor in it, the magnetosphere plays a big role. So without a magnetic field, it's possible you lose a lot of your volatile hydrogen. And her hypothesis has been that Venus and Mars have lost their hydrogen that way. They don't have a magnetic field. The solar wind can strip it away. So that right there would tell you, boy, maybe a dynamo is important if you're going to want water around. That's, as I said, that's a hypothesis, and I don't know too much more about how people feel. It's contested, but that would be one of the ingredients I think people should think about in talking about exoplanets. But I think the whole field of thinking about exoplanets and their space weather and space climate, something we want to talk about here, but it's not a field that has a long history. Yeah. Mm-hmm.
So as like a
Yeah.
yes,
Yeah.
the field is needed or not.
Yeah. I didn't mean to imply it wasn't complicated, yeah. But there's certainly a role for the dynamo to play in the habitability of a planet, we think. Diane. Yeah. Oh, that's, boy, we're going to have to discuss that over lunch. Is there all kinds of flares going on at the core mantle boundary? As I said, I don't work on that. That's an interesting topic to think about, what's going on in the restructuring of the magnetic field inside the Earth. Uh-huh. Right now, there is the Earth's magnetic field is changing more rapidly now than it has for a while. It's possible it's reversing. I'm not sure everyone will agree to that, but it is definitely changing more rapidly in the last 20 years or something than. Oh, yeah. That's interesting topic for discussion. I can't add anything to that. Yeah. my suspicion, and it's nothing more than a suspicion, is the turbulence is, well, no, I think there's an answer to that, and I'm going to declare ignorance on that. We should all think about it. Yeah, that's right. There are many sun-like stars that have a very chaotic magnetic history. Yeah. As I said, they're definitely operating in different, I would say, the different Reynolds numbers and magnetic Reynolds numbers are going to be part of that explanation. The Earth's turbulence is at a very low Reynolds number. In a way, turbulence at low Reynolds numbers is more chaotic often than at high Reynolds numbers, which is one of the reasons when you make a golf ball, you put the little dimples on it to create very small length scales and therefore high Reynolds numbers and therefore much more predictable turbulence. Although, if you've ever seen me play golf, you would not describe anything I do with a golf ball as predictable. But when done right, the high Reynolds number turbulence is a little more predictable that way. But that's just one example. But I can't answer. It's a good question. We should probably all break for lunch. We can talk more about this over lunch. And I will see you at 1:30.